All right, hello. This objective is about working with surface area and volume, but now affected by scale factor and in context. Okay, so as always, we'll start with our important vocab. So surface area is the space inside a solid. Oh my God, not inside. Whoa, my bad. Space outside a solid. Whereas volume is the space inside a solid. And then to compute, SA will stand for surface area and V for volume for these different types of shapes. There's lots of formulas. So a prism is like when you have like a 3D box situation, like this, okay? Surface area is going to be 2 length width plus 2 length height plus 2 times width height. Okay? Volume is just length times width times height. Okay, for a cylinder is like this shape. That guy right there. Okay? Surface area is 2 pi r squared plus 2 pi r h. Volume, we can get that by doing pi r squared times the height. A cone looks like this. Okay, surface area is pi r squared plus pi r s, where s is your slant height on that slant there. And then volume is 1/3 pi r squared height, where height is again how actually tall the object is, so not being on that slant. Okay? Sphere, surface area formula is pi r squared. Volume formula is 4/3 pi r cubed. Okay. Reminder. So we're going to actually get back into similar figures with scale factor. Similar figures are figures that have the corresponding sides are proportional. And their corresponding angles are congruent. But we're really going to be thinking about the sides. So I'm just going to write that down. Corresponding sides are proportional. And then your scale factor tells you it's the ratio of the corresponding sides. Okay, so it's like the factor that changes the two similar figures. So here, I'll draw a little example up here. So if I've got a rectangle that's like 2 by 3, and then if I were to multiply it times 3 and get 6 and 9, the scale factor for that would be 3. Okay, cool. So we're going to jump to our first key points box. So where we're going to deal with surface area, volume, and scale factor. So let's start with example 1. The surface area of a solid is 100 inches squared. If the dimensions of all the solid are halved, what is the surface area of the solid? Okay, so basically we're taking this, some solid, we don't even know the shape, right? And we're like, okay, if I make all of the dimensions half as big, what's the surface area of the new solid going to be? Now, we could like play with some numbers and like actually like take the dimensions of this shape and divide them in half and calculate the new surface area. Or I'm going to tell you a formula that will actually do that math for you, okay? So basically, if all dimensions, so the side lengths of a shape with a surface area called SA are changed by the same scale factor, K, then the surface area of the new shape, we can find it by taking whatever K is, squaring it, and multiplying it by the original surface area. Okay? So we're going to do that here. The surface area of the solid is 100 inches squared. So SA is equal to 100. Okay? If the dimensions of the solid are halved, so K, my scale factor, is going to be multiplied by 1/2 because of the word halved. What's the surface area of the new solid? It's really easy. We use this formula, K squared times surface area. So I'm going to do 1/2 squared times 100 1 divided by 2, or 0.5, whoops, squared is 0.25. So that becomes 0.25 times 100. It's going to equal 25. Okay? Let's look at the next example. The volume of a solid is 100 inches cubed. If the dimensions of all the solid are halved, what is the volume of the new solid? So, very similar question. The new thing is just now like this is volume instead of surface area. So, again, instead of us like playing with numbers and trying to actually like figure this out by like calculating the whole volume of a new solid, I'm going to show you a new formula again. If all the dimensions of a shape with a volume we're going to call V are changed again by that same scale factor, that we're going to call K. God, that's a K, you guys. Okay. Then the volume of the new shape, we can find that by doing K cubed times the surface, or sorry, times the volume. Okay. So, same thing. So the volume of the solid here is 100 inches cubed. So V equals 100. If the dimensions of the solid are halved, so K is going to equal 1/2 again. What's the volume? Well, let's use our formula. V equals, the new solid. We can find that by doing our scale factor K cubed times the volume. So let's take 1/2, we'll cube it, times our volume of 100. So 1 divided by 2 to the third power is 0.125 times 100 equals 12.5 inches cubed is going to be the volume of that new figure. All right, a couple more examples. Example 3 says, the rectangular prisms below are similar. If the surface area of the smaller prism is 40 meters squared, what is the surface area of the larger prism? Okay, so, let me see. We want the surface area of the larger prism, so of this guy, and then it says the surface area of the smaller prism is 40 m squared, okay? I'm also noticing that they give me 2 dimensions, okay? So in order to use this formula, I'm already given the surface area of the smaller one. So I can use, I have this part, right? So surface area is going to equal 40, right? I need my scale factor. Well, I can find my scale factor by comparing my new over my old. So my K is going to be equal to 6 over 4, which if we care, that's 3/2. Okay, remember I can divide it's the ratio of those corresponding sides. I can divide my corresponding sides to find K, and now I can do my formula. I can do 3/2 squared times 40. So that's 2.25 times 40. That's going to equal 90 meters squared. Okay. So extra step there is I just had to I found that scale factor, right, by dividing my 2 corresponding sides. Right, that's how I figured out what K was. Cool. Let's look at example 4. The cylinders below are similar. What is the ratio of the volume of the larger cylinder to the volume of the smaller cylinder? All right, let's figure this out. What is the ratio of the volume of the larger cylinder to the volume of the smaller cylinder? All right, well, let's figure out my scale factor. Well, let's look at what we're given here, okay? We're given 2 heights. So again, I can do the ratio of those corresponding sides and divide. So 24 over 18 is going to give you my K again. I'm going to reduce it. Okay, and you get 4/3. All right, so what I can do is I can take, if I just cube this, it's going to tell me how the new volume is going to change. So if I take 4, because k cubed times the volume is what's going to happen, right? So if I just do my k cubed, it's going to equal 4/3 cubed. Use my calculator to figure this out. 4 divided by 3, and then to the 3rd power. That's how much bigger the bigger cylinder is going to be, okay? It's going to be essentially 64 over 27, so like that comparison, okay? Cool. Let's move on to our next key points box. Okay, last we're going to talk about finding scale factor if we're given surface area or volume, okay? So before we get into that, let's remind ourselves what our rules are around that. If all dimensions of a shape with the surface area, again, SA, are changed by that same scale factor, K, then the surface area of the new shape is K squared times the surface area, right? Let's talk about with volume. If all dimensions of a shape with a volume V are changed by the same scale factor, K, then the volume of the new shape is K cubed times the volume. Okay? So, the following solids are similar, where the larger figure is the transformed solid. What is the scale factor? So basically, I can use this idea here. I can be like, okay, well, to get that new surface area, I'll call that N for new, okay? The surface area, basically, whatever the scale factor is, K squared, was multiplied by the surface area of the original figure, right? So basically, we'll call this the original, because it wants where the larger figure was the transformed one. So like, wait, the solid instruments are similar where the larger figure is the transformed solid. Oh, I'm sorry, it's going to be backwards. Am I reading this correctly? The larger figure is the transformed solid. So this is the one that was transformed. So yeah, this is the original. You're right, I'm sorry. This is the original. And then this is your new one. We transformed to get here, okay? So, what happened? Well, 1377, that surface area times a scale factor times the surface area of the original, which is going to be 68. Okay? And then I just got to solve this. So how do I solve this? I'm going to divide by 68. And get 20.25 equals K squared. Yeah, okay. And so then the scale factor, and I took the square root, and that left me with K equaling 4.5. Okay, so basically this figure is 4 times the size of that figure. Okay, so basically what I did here is I just plugged in the surface area. Okay, and we'll see in a second what we could do with volume, and then I'm solving for K. We'll come back to this in a second, okay? Let's do one more example. The following solids are similar, where the larger figure is the transformed solid. What is the scale factor? So again, we've got our original here. And then the new one is here. This was, we transformed to make this happen, okay? As it says, the larger figure is the transformed solid. Okay, so what is the scale factor again? Well, now I'm going to use volume, and I remember that to get a new volume, that can happen by doing k cubed times the volume of the original. Okay, so my original is 21 times whatever my scale factor cubed is going to equal my new volume of 10,752. Okay, so now I just got to divide by 21 to solve this. You get 10,752 divided by 21. You get 512 equals k cubed. I got to find my cube group symbol. Okay, and you're going to get k equals 8. After I did cube root there to get to 8. So this is now 8 times the original. Okay, so then basically all I'm doing here is I'm plugging in the surface area or the volume of both shapes into these rules here and then solving for k. And that's it. Hope that made sense.